Hello, everyone, and welcome to this Oracle Machine Learning Office Hours session, Machine Learning 101 Feature Extraction. We'll be hearing from Marcos Aranzubia and myself, Mark Hornick, Senior Director, Product Management. So for today's agenda, we'll just mention briefly our upcoming session, and then Marcos will take us through a very exciting introduction to feature extraction, as well as notebooks highlighting the various techniques. If you have questions, we're happy to take those in the Q&A section, or afterwards we'll have time for interactive questioning as well. So the next session is targeted for January. We haven't specified a date yet for that, but it will be Machine Learning 102, Feature Extraction, and this will be the 8th session in the series, and we'll continue to learn about methods to extract attributes from large numbers of columns in data sets. So we'll target the explicit semantic analysis and some of the benefits of feature extraction as a data pre-processing step for machine learning models. For more information on Oracle Machine Learning, you can go to oracle.com/machine-learning, and there are a variety of resources for you to check out there. If you would like to try out Oracle Machine Learning in Autonomous Database, there's the Oracle Cloud free tier, and you can get a free account for that, and the terms of that are identified here and also on the website. So please go to oracle.com/cloud/free. And with that, today's session, Machine Learning 101, Feature Extraction, we'll be talking about the various methods to extract attributes from large numbers of columns of data sets. It's dimensionality reduction is the problem that we'll be tackling in this. And so with that, I'll turn it over to Marcos, who will take us through this very interesting topic.
Thank you very much, Mark. Hi, everyone. So today we'll be talking about feature extraction. Basically, the idea is feature extraction involves trying to reduce the number of resources required to describe a large set of data, right? And on the right-hand side, you can see where in the cycle of building models, right, and preparing the data, the feature extraction is going to fit. So it's really a data preparation step, and then it goes to modeling, and usually you go back to data preparation, or you go back to the feature extraction settings. You adjust the number of attributes you're working with. And you guys are going to see in an example today why those things normally are really a cycle, right? So the term feature extraction is really used to denote it's really a family, right, of different methods that you have to try to extract, I would call it, the most information possible from a data set, right? So in other terms, right, if you think about statistics, normally we call it in search of variability, right? Because when you're trying to identify things, when you're trying to classify things, right, a good customer and a bad customer, you want the most variability possible on your attributes so that you can separate people, right? You want to be able to bucket people in different places. If everyone has the same age, if everyone has the same gender, if everyone lives on the same city, you don't have that separation. So you won't be able to say, why is this customer good and that customer bad? Because they all have the same attribute, right? So at that point, you don't have any ability to separate those things. So in general, it is part of this pre-processing. And feature selection, it's part of the capabilities of the feature extraction tools, but it's not really only for that, right? So, but feature selection is what we're going to be looking today in more details, right? So feature selection, it's also known as, dimensionality reduction, variable selection, attribute selection. There are many names that people give to these things, and that the idea is you select a subset of the attributes or variables or predictors, right? When you're trying to create a model. So the benefit here is really simplification of the models, right? So if I need to, instead of using 2,000 different attributes to predict your likelihood to buy a product, I can get by with 5, my model is going to be much faster to build, and my scoring is going to be much faster as well. So, and not only that, that can create a more stable model, right? With 2,000 variables, there might be variables there that are, varying because of like external agents that you don't even, understand well, and then you would not have good control, so your model would not be actually good over time. So, in addition to that, there are some methods, right? If you think about, and we saw in classification, random forest, we saw logistic regression with feature selection. So there are several methods that can do automatic feature selection as well, right? So there are the algorithms that can do feature selection as a component of their natural computation, right? And then there are other methods like the ones that we're going to look at today that look at the natural dispersion of the data, and they try to help you by selecting the features that you could use. So in terms of the algorithms, right, some of the methods that are included here, and again, this is not a complete list, right? So there's a lot of methods, lots of different methods. These are some of the ones that we talk about and that we include with Oracle Machine Learning. So we have an attribute importance algorithm that actually uses the minimum description length for the processing, and then feature extraction methods that will do some sort of transformation, translation, rotation of the axis of the original attributes to try to get them into a position where you would see the most variability. And we're going to look into those. Things like principal component analysis, single value decomposition, non-negative matrix factorization, and the CUR matrix decomposition. Those are things that have some similarity in terms of their approach of trying to decompose the original data into separate set of matrices. But also the one that's used for NLP, for a lot of text mining, is explicit semantic analysis. So we're going to look more into details of ESA in our 102 session in January. So the idea is that using these transformations, right, or simply excluding these variables that have low relationship with the target that you're looking, it's always, helpful, right, to build predictive models. And because a good data preparation is normally 90% of the work, right, so the actual machine learning modeling is really the end of the entire process, right? Then you would probably see that feature extraction might be a key element here. So the basic attribute importance then for Oracle, right, what we do is we compute a relative importance of predictor variables versus a target. It is a very simplistic method because it's going to use a pairwise, or it's going to check what's the capability of this single variable to determine the outcome, right, of your target. So it's going to do a 1-by-1, but it's a very simple, very fast to run. You can gain insights very quickly on millions of records with these kind of attribute processing. And we have, by default, the minimum description length as an algorithm on our Python interface. And the SQL interface has the CUR matrix decomposition as well available there. Now, the idea with this is it supports both categorical and numerical targets, so it can work very well on both, right? So for us, in the Oracle Machine Learning, it also includes auto data preparation, so normalization and binning is there. You can allow or ignore missing values. You support the partition model build. So there's a lot of things there. The only thing that the attribute importance does not do is that it doesn't have a scoring action. So you don't really predict using that model, right? The output of that model basically is, these are the relative metrics indicating how much a variable contributes to predicting target, right? So values more than 0, right, will contribute to prediction. Very small values do not contribute or just add noise, right? So another method that is used a lot is the single value decomposition, so SVD. It is a feature extraction algorithm, and what it does is actually tries to find these orthogonal linear transformations, right? So it will try to look at the matrix and look at the data, and if you think it as a volume, right, it's going to move the data around to try to find what is the axis with the largest variability, and then it creates a second orthogonal axis to that and find what's the second best um, positioning, right, that it can take to take the most variability as well, and it goes on and on. So you're going to see an example when we talk about it, and it supports in our case, in the Oracle machine learning case, we have several eigensolvers. We support Y data, we support tall and skinny solvers. So we have all of those some of these more stochastic solvers to support very large data sets, but we also have the traditional SVDs for more stable results as well. Another method is the non-negative matrix factorization, right? It's a mouthful, but it's easier to say NMF. So the NMF, it's really a state-of-the-art algorithm for feature extraction. It's very good. It does dimensionality reduction. It creates new features, and you can check the attribute importance, right, for each of the contributing features to each of the vectors. So you would take a subset of that attributes that you find for each of the vectors that come out. But it differently than SVD, NMF is not really orthogonal, so it doesn't build orthogonal planes. There are techniques called the orthogonal NMF that do that, but the NMF by default doesn't do that, and you will see also how that works on the demo that I show you guys. And finally, it does support text mining, so life sciences and marketing applications, it's is very widely used. So an intuition on NMF then is basically that it's very useful where you have many attributes, of course, and then some of these attributes might have weak predictability by themselves, but then when you combine them, then they will give you meaningful patterns, right? So in the text, you can think about the word hike, for example, right? So if you think about a word hike, the NMF can introduce the context. So, it can actually introduce the hike and mountain to be an outdoors sports, and hike and interest, then it can understand and it can help you identify that it's an interest rates, right? So it gives you that kind of ability. So in general terms, what it does is, you have the attribute values on the left, and then you have your target values, but it adds these extracted features in the middle, right? And the features do not have necessarily all of the attributes, right? And the attribute values coming in from the left. So you see that some of them are there and some of them are not, but they're not totally connected, right? And then you project those features into the target values. So one interesting use is actually face representation, right? So if you think about image representation, there are some methods, right, for face representation. So one of these methods, for example, vector quantization, basically chooses one, right? It picks one that is the most generic one there that it can find, and then that's the process, that's the idea that it does. Then people moved on to principal component analysis, right? So PCA, much used for image, and especially is good at edge detection, right? So it will run there, and then it will find, okay, what's the kind of encoding that you see, and then it identifies all of these different edges, and then it builds that, so the reconstruction is that on the right. So it's better than vector quantization for sure. And then what NMF can do is actually, it goes a little over that, so it improves on top of what PCA can do, and then you can get an even better reconstruction of that image. So we're going to take a look at some examples, not on image recognition and faces, but on our basic data and our classification models that we were doing, and you guys are going to see how that fares, right, with all these different methods. Also, a quick comment on explicit semantic analysis. So ESA is really a specific model for being more interpretable than the latent Dirichlet allocation, or LDA. So in NLP is very much used. We're going to look in more details into what ESA can do in January, where we're going to be playing with some of the document similarity and looking at text. So having said that, let's take a look at the demo. So right here in our notebook, we're basically taking a look then at feature extraction. And the idea is going to be, we're going to take a look again at basic data processing, so understand what data set we're going to use. Then we're going to go and do an attribute importance using MDL, right, the minimum description length, as we talked about. But I'll be doing a feature selection, right, using the attribute importance. So we're going to decide, say, a cutoff right in there. And then we're going to compare a GLM model, right, a logistic regression, with a reduced set of attributes chosen by attribute importance, and we're going to see how that fares. Then we're going to move to SVD. So the singular value decomposition, in our case, we also put PCA in there because they are so similar. We are able to create the principal components as an output and score principal components out of our model. So we're going to look at that. We're going to build a SVD model, do feature selection again, compare with GLM, and then we're going to build the principal component projections. So because we do that, we're going to be able to do a comparison, a visual comparison in 3D on how is the SVD and PCA actually working on top of your original data set. And then finally, we're going to move into NMF. We're going to build an NMF model for attribute selection. We're going to understand the relationship of these attributes versus the main NMF feature vectors. Again, do another feature selection using NMF in this case. Compare a GLM with a reduced set of attributes, right? And then use the NMF for prediction as well. So, and look at the NMF feature projections, okay? And then finally, we're ending up with the comparison of that in 3D. And we are going to have the at the bottom, at the end of everything, we're going to take a look at the logistic regression with the feature selection enabled by itself. So it comes with, right? So to see how that fare against our intuition on the other algorithms, and an AutoML as well with feature selection and model tuning for logistic regression. Okay, so basically the data set we will use is the one that we used before when we were doing classification 101. We used the breast cancer data set, right, where we have features that are computed from digitized image on the fine needle aspirate of breast mass. The original data set has 31 attributes that includes the target, right? And the target is 1 for malignant and 0 for benign tumors. And we will use all columns, and then we'll select the best columns by each technique, right? So the basic initialization of the environment, connect to the database, loading that data set from scikit-learn. So I'm just basically saying load breast cancer, right? And then at that point, I do an X and Y, and then I push the data set to the Oracle database, right? So if there is a table called breast cancer, I drop it, and then I create a breast cancer data set by pushing a pandas data frame, right? That's concatenation of the X and Y. So it's a very, very small data set, 569 records, 31 columns, right? So exploration, I think you guys probably seen this before, but the idea is you have the data set here, and then you have all of the data set contents here, right? So mean, medians, radius, texture, perimeter, area. So these are all features, right, on that image about that breast cancer. And then all the way to the right at the end, you have the target. It's a malignant or benign, right? So for data visualization, well, let's take a look at some three variables, right, or 2 variables at a time. So data visualization in Zeppelin on the left-hand side, you can just do, Z-show to look at the local data. On the right, what I'm doing here is I wanted to take a look at a 3D plot, so 3-axis. So I wanted to take a look at worst perimeter, worst radius, and worst area. And then on top here, I built a simple grid with the z equals 0, or to try to get a reference, right? Actually, I'm doing z equals 1000 here. And just to give you an idea, right? Because I really rather put this grid so that you can see that the original data, at least for these 3 columns, right? It starts on the bottom and then it crosses this grid and goes all the way up, right? So it's just to give you a visual. So you see the data is not really straight line on any angle here, right? It's just going straight up and perforating that plane. So let's run the attribute importance then. So to build an attribute importance model, on the left-hand side, you see that we have we are splitting the target, right? So the X and the Y. So I'm dropping the target. So I'm splitting the data set into the target column and then all the other columns. I'm just going to say sampling disable because I really want to, the data set is small enough. I want to run it in the entire data set. And then I call the model fit, right? So I'm doing an OML.ai model, right? That's attribute importance. And then I am fitting that model. So the result is something like this, which is it tells me the function, right? It used the MDL, right, as a setting there. And then this is the output. So I got statistics. It tells me all the attributes that were coming in. And then it spits out the importance, right? So I get a variable importance, and then I have the ranking. And you can see that there are a few variables with 0, right? That means they're all tied for the worst variable to use on your problem. And it's not uncommon to find lots of variables with 0, right? Sometimes you can try to put what's the color of the eyes of your patient. It would probably have absolutely nothing to do with the size of that breast cancer mass, right? So there are times where you are going to find 0, and that's fine, right? So on the right hand side, I can see the same exact object, right? This is the same model because the model now is that AI mod object. So I'm just pulling the importance here, right? And I want to sort it by importance, right, to make sure that everything is fine. So I can see the variables there. So I have worst perimeter as the one with the highest importance, worst radius, worst area, worst concave points, and mean concave points, right? Things along those lines. So, and then, of course, you go all the way down to 0. But the idea was that we were going to get only a few of these, right? So we're trying to reduce the amount of our analysis. So let's do a simple comparison. So I'm going to basically now prepare train and test data, right? So I get my train data and my test data. I'm going to split the 60-40 here. So now I split that data into training and test. And I'm going to run a default logistic regression with all attributes, okay? So I take the default logistic regression. I'm just saying classification. This is the X. This is my Y. And when I predict, I'm going to predict the test, right? So I'm going to see how did it do when trying to predict my test set by using this GLM model built on the train, right? And I compare the accuracy. So I'm going to be very simplistic this time and just going to print out the accuracy, okay? So I'm just printing out the accuracy, very clear. You guys can see, right? 92.04%. That was the accuracy of the logistic regression model using all attributes. Now, if we are saying that the models do not necessarily have everything, right? So I'm saying there are attributes here. There are lots of zeros, right? So that's noise. And there are attributes with very little importance. So what about we take that and now we select manually a few of those guys. So let's take the top 10 attributes or the top 5 attributes and build models and see what happens. And look at that. So with the top 10 attributes, you go up in accuracy from 92% to 94.69%. Now, if you want to save even more, then you can go to 5 attributes, but then you go down a little bit in accuracy, right? From 94.69 to 94.25. So what we have learned right here is that even though we want to do big data, we want to say, I want to include every little bit of data, information that I have available, and I want to throw the thing at the models, right? If you don't do feature selection, you might be doing it wrong, right? You will potentially be losing accuracy because you're adding noise to the model that is unnecessary, right? So again, this is going to be a finer process, as you can see, right? Because I manually selected 10 attributes here, and then I manually selected 5 attributes here. So what's the best one? Well, you're going to, that's up to you, right? Up to your problem, up to you, up to looking at what is the exact or the best number for you to get to, right? But not all is lost. So let's move on to the next algorithm, right? So SVD. So let's take a look at how SVD helps us, right? So let's build an SVD model, a singular value decomposition model. So you build the SVD model, right? And then I'm showing you the code here. So we're going to create an SVD. All we're doing is just enable the details and auto data preparation. As you guys remember, it's automatic. Normally is on, is the default. But I'm adding one special twist here to my SVD, which is the scoring. I want that to do PCA scoring, okay? And we're going to see how that works. So I'm going to want to build that model, and now I'm going to fit that model, and then I'm going to say, okay, that's that's my test model, right? So it builds the model for you, and then you get the output here. So all the tolerances and all the different processes, global statistics, the attributes. Then it comes out with features, and then you get all the matrices, right? So you get the D matrix that has some feature values here, right? So these are the singular values that come out of the feature, just to give you an idea of the importance for each of the features that it came out, right? And then you get a listing of all the columns. So all the columns versus the features as well. So in any case, it's probably easier to look at on the right-hand side here. So what I have is, again, the same feature ID, right, that I got, the value, and then I added myself a percentage just so that I can keep track of the size of the model, right? So this does not mean percent of variability, just like PCA would mean. So these are not the eigenvalues. These are the singular values from SVD, but they can give you an idea of the power, right? So obviously, right here, if you go all the way up here on our computed settings, it's going to tell you how many it suggests. So I'm going to decrease the font size for a second here. This is what the SVD model is suggesting. It's suggesting the cutoff at 1. By 1, it means take the feature ID number 1 and forget about the rest. You might not need the rest. That's what it's telling you, because it contains the most amount of information on that model. So on the right-hand side, then, I have that the singular values, and I'm just graphing them so you can see that difference, right? So it's really large, the difference between those singular values. So it might be a good idea. Another idea could be there might be some information here on the other one, because it has 10% of the total information, right? Sorry, of that the total variation or information expected from there. But let's take a look then at what we can see. So because we get the attributes, right, with feature vector, then I want to take each feature vector, right? Now I'm taking each feature vector and I'm going to say, if the feature ID is 1, show me the attribute and the value related to that feature vector. So remember, feature vector 1 contains 80-something%, right, of the total information, and SVD suggesting that I should only keep that. So I look at this guy and I see what are the attribute names here, and they're different than the attribute importance, right? I have a worst area, mean area, and then I have area error right here, right? But also, when you think about these kinds of things, you got to be careful, because now this number is not necessarily bad when it's low. This is really a correlation to the feature vector. So if there is something strongly negative, it would also be good. In this case, there's not, right? There's a small negative there. So, but because it's the correlation, so that only means, the bigger the worst area, the bigger the feature ID 1. If this was a minus 0.8, it was going to be good as well, right? Because it's still very well correlated. It's negatively correlated, which only means the larger this number, the smaller the feature ID 1 on the other direction, right? So there are information there as well. So in this case, this is a feature vector 1, but I said, let's take a look at the 3 first ones. So feature vector 2, and because this method is orthogonal, you're going to see that what happens is the variables that are most related to the number 1 is not going to be the most related to number 2 at all, because because of the way it is, right? Because of that orthogonality. So then you got mean area, and then you got mean perimeter, right? Which is the second best one, even though this one is okay, right? Mean area is 85% correlated. And then mean perimeter is already only 6% here. But now, if you go all the way down, now you have the worst area here that is also correlated negatively with this guy, right? Which again is okay, as we mentioned before. Now, if you go look at vector 3, then a feature vector 3, you also find what are the things that are correlated to it. So now, because of the way it is, there's not a lot of information more left. But the area vector is very well correlated, but all the rest is very tiny here, right? And then potentially you're going to find not even that, not even a negative. So that's why, the SVD by default, the result is saying, yeah, just keep vector 1 for you. So, okay, so let's do that. Let's compare, right? Again, a logistic regression. So let's take a look. Let's take the top 7 attributes from feature 1. Okay, so I'm going to take the 7 best attributes here from feature 1. I'm going to take the top 5 attributes from feature 1, and let's run it. So now that's very interesting. With 7 attributes from feature 1, I get 95% model accuracy. If we go back, remember that we were getting 94.69, right? That's our best here on the top 10 attributes in attribute importance. So we get 95% accuracy, but then if I leave stuff out, so if I only take the top 5, I lose accuracy. So I actually need those top 7. Another way to put it is, what if I take the top 4 attributes from the top 3 features? So that means take this top 4 and then continue looking at the top 4 here, as long as it's not here as well, right? So mean area is there and mean area is there, so you don't need that guy. You'll take the top 4, so you get the other 3, right? So doing that kind of process, you still don't get the greatest accuracy here. And we're back to 92.2 when we combine these ones here. So for now, this guy is winning, right? And as I mentioned before, because the SVD model can be used for prediction of principal component projections, then I decided to do that. So I just remove that. I create this guy in SQL. So this guy uses SQL to do that. So I create the PCA projections. And I'm selecting the top three, right? Worst area, mean area, and error. That's the top three variables right here, right? So I'm selecting those three just so that we can visualize what is the model trying to do, right? And then we're going to look at the projections. So the projections are going to be numbers like this, right? So they might not mean much, but that's what they're doing. So for every record that we get, you'll see the PCA projections here. So of course, being a more visual person, I wanted to see that and look at that in the space. So let's take a look at the original data. So the original data, remember those three best variables, right, that were decided by the SVD. So the original data is going to show up here, and it's going to be the worst area, the mean area, and error, right? So you can see that, I just drew a plane through the bulk of the data here so that you can see what happens, right? So when you do that, you see that the data spatially, right, it's kind of like flat in the bottom, but then it goes straight up. It's kind of like a weird diagonal, right, shape. And looking at it all from the top, you can see that it goes into this diagonal, right? And then things go all the way up. So that's the original data. What is SVD or PCA in this case trying to do, right? They are trying to find a new plane, right? They're trying to take this cloud and twist it in a way where the variability is the maximum possible. And then they're going to try to cut this through. So probably, if you can imagine already, right, this guy's going to be something like that, right? So the plane that the process is going to take is probably the component number one on principal components is going to do something like this, right? It's going to try to maximize the distance between these points. So it's going to go through something like that. And then the second component is going to try to find the other axis. So where is the widest possible side of that cloud, right? And so on and so forth. So let's take a look at what happens. So in here, you can compare what happened, right? So as I mentioned, the principal components try to find a plane through the maximum width, right, or the maximum length. So if you look at on the top, that's basically what it did. It actually twisted this original thing on its side, more or less, right? And then it determined that this is the best and this is the first principal component. So this, from this point all the way to that point, is where you got the maximum variability possible. The second principal component down here is the one that shows me the second maximum variability over there, right? And then the third one, which is this one, is showing me these other points that are kind of like out of order here, but these little points here, right? That's the third component. So this is just to show you what the methods are doing, what they are doing in a physical way, right? They're taking your cloud of points and they're trying to twist it around so that they can find the maximum variability, so that when they do that, then you can assume, yeah, that's the best possible range, right? And then what are the variables that are the most correlated with this projection, right? That's basically what it's doing. So the scatter matrix plot as well it might be useful. And side to side, you see the original data on the left, and then you see the projections on the right. So one thing to have in mind, though, is that the projections here were not only created using the three attributes, right, on the left-hand side. The projections were actually created using 30 variables that you had, right, originally. So this is just telling you this is the best we could find out of those, and then these three are the most correlated with these guy, the number one here. Okay. So moving to non-negative matrix factorization, then what we have now is the SQL interface. So we have to use the SQL interface for this for now, and then but it's very simple, right? In SQL, you're going to build your non-negative matrix factorization model. That's the name of the algorithm. Then feature extraction is what we want to do. And I'll bring in the breast cancer NMF. The breast cancer NMF is just because I created a view that does not include the target, just to make it easier on myself. So I created that view that there's only one variable that is not included, which is the target, and that's the easiest way for me to represent it over here. So when the model is built, then in SQL I can check a few things. I can check the model settings. So I see that those are the model settings that were used, right? So automatic data preparation, missing value automatic, number of iterations, and things like that. On the right hand side, the model signature is going to show me basically what were the variables that it used, right? The variables used as input. And then there are different NMF views that we can have, right? So these are the different things that come out of that model, right? That are stored in the database with these specialized view names, right? Now, looking at the specific test model, so this is what it's doing. It's basically telling me that you probably want to use 3 features, right? Maximum out of the NMF here. So those are some things that I'm going to check. So let me first take a look at the relationship of the attributes and the feature vectors, right? So feature vector number 1, 2, and 3. Again, I'm using SQL. It's the same process I did before, right? Where I say, what is the feature ID I'm looking at? And then show me the attribute names and the coefficient, right? So just as before, I'm looking at the feature vector and the coefficient of each attribute against that feature vector. Now, you can see that there is a very distinct thing here happening, which is NMF not being an orthogonal, right? So it's not that radical of a difference between all of the attributes. The attribute coefficients go down smoothly, right? It's not like that jump that we saw before. In this case, it's going to 0.29, 0.27, 0.25, 0.24, and it's just the nature of the algorithm of NMF, okay? So it will go down again. Same thing is going to happen. It's going to eventually get to the point where you have almost nothing there, right? That's the main idea here. And then the same thing is going to happen, feature vector 2, right? And the feature vector 3. So same process. You're going to see these guys going down, not necessarily to 0, right? But they're going down to a very small number, right? So let's try to use, again, logistic regression. How good it is to use NMF on my logistic regression, right? So let's take a look. 7 attributes from the first feature 1. Let's take the top 5 attributes from feature 1 again, just like we did before. And voila. This is the best model we have so far, right? So 97.35% accuracy. So I got a 1 feature vector on NMF, and I took the 7 top attributes, and I got 97%. Again, I decided for the top 5 attributes, and I only got 92%. So all that means is, again, it's something you will have to do, right? You'll have to come out here and say, yeah, let's put a cutoff here. So by 7, I meant 0.2, right? 0.2 and over. So that is something that the end user will probably have to take a look and play with. And then if I did the same thing, I took, what about the 4 attributes from the top 3 features again and get that mix? Not bad, but still not 97, right? 95.558%. Okay, so because, again, NMF also has their own feature projections, right? So I want to say, okay, let me check that I created with SQL, and I got the feature values out of that. So let's take a look at the projections, right? So NMF projections, right? The range is very different than what we had with the PCA, right? You can see. And then the interesting thing here is that the projections, because they're not orthogonal, remember that they are not orthogonal, right? So you look at the original data. This is the original data that we have there. And then if we plot the first three feature vectors, this is what happens. So this is the original data for the three top variables defined by NMF. So NMF used these three variables, and it says these three variables are the ones that can give me the most information, right? That was the decision NMF did. So you don't see those crazy outliers like we saw before, right? It's a little more dense here. But when you look at the vectors, right, the feature vectors, is definitely different. So it's not that straight line. If you guys remember, the SVD and PCA, because they are orthogonal, they are looking for planes and to cut off, right? This is not, right? The NMF is not looking at those planes. So is rearranging the location of the data, right, in its own way. And you can see that it is an interesting combination, right, between the features that is probably going to give you the best analysis here. So again, just to look at the top three attributes and the feature vectors, right? Now you can see that kind of distribution, right? So the kind of transformation that this NMF ends up doing, right, to the data. So to finalize, remember that I talked about each of the methods having their own feature selection, but also AutoML, right, is one method that does have that. So let's take a look. So logistic regression, I am turning on, right, a feature called the feature selection enable, okay? And that's a setting that I can turn on for GLM. And I'm giving it as input everything, instead of just limiting the number of columns or attributes that I'm analyzing. I'm giving it the entire data set, okay? And I'm letting it choose itself what the columns that it will like to do. And then I'm predicting on the test data set, and then I'm checking accuracy. And that's what I got. So the logistic regression itself, after the feature selection, was able to give me a 95.13%, right? And I can add potentially add them. I think I can add the model here just so you guys can take a look at the output. So looking at the output, then when we look at it, right, that's basically what it's saying. It used the Cholesky solver. It used the GLM Ridge disable, because then it was doing feature selection. And then here are the attributes that it chose. So it picked up 1, 2, 3, 4, 5, 6, 7 attributes. And then these are the estimates and the fit details there. So that's basically the what it was able to do, right? So not far from our 97, but still not the 97, right? And that's just interesting to me, that whenever you can use feature selection from an algorithm itself, probably, yeah, it will be great, right? It's simpler. It's one command. You don't have to worry about what's happening, and you see the output, and it explains to you why those columns did not make it. But it's also interesting to note that NMF was able to get me 97% accuracy, right, by letting me pick and choose manually the variables related to it. And then we go to AutoML. So AutoML, with AutoML, I can give it the data and I can let it run. It will define what are the best models. So it picked up the neural networks model here, and then it picked up a GLM Ridge. So just to compare apples to apples, I just picked up the GLM Ridge here, right? And then I ran it, but I gave it the I let it run with the feature selection in AutoML itself. So potentially, it's already indicating to me that maybe the neural network would have been the best model for this problem, right? but I want to compare apples to apples. So I want to compare the logistic regression and what's the best logistic regression that AutoML could have given me here. So it's telling me the features that is selected and auto tuning. So I tuned that guy, create the prediction output for AutoML, and then finally I get the prediction. So it gives me 95.58%. So it is a little better than just the plain old GLM feature selection enabled, for sure. But you can see that it still wasn't able to get to the 97%, right, accuracy that I was able to get myself with the use of NMF. So again, I think that the idea is, and what I wanted you guys to come out from the session with is that feature selection is very interesting, important for you to do. Feature extraction has some very cool techniques that might give you great ideas, and that even if you work a little bit more manually on those things, you might get a great output as well. So with that, I'll go back to my slides, and that was it. So for more information, as always, oracle.com/machine-learning, and I'll open up to Q&A.
Well, thank you, Marcos. That was a great session. And we have a number of questions. One that we'd like to revisit had to do with how did we arrive at the feature ID and the respective list of features? This originated initially when you were showing the SVD model. Could you say a little bit more about, where did these feature IDs and the actual features come from?
Sure. So what happens with the models? I think SVD, right? You were talking about. So
yes.
all of these methods, what they do is they in the output, right, of the method, and let me. I think I'll make this a little bigger so that it's easier for you guys to see that. So the output of any of these methods, SVD, PCA, right, NMF, is that in the output, when it's building the decomposition of the matrices, then as an output, this is what it does. So it gets the feature ID, and then from 1 to 25, in this case, because 25 was the arbitrary limit on the settings, I didn't change it. But what the methods are trying to do is they're trying to project or trying to extract from all of your data the most significant feature that represents the largest variability, right? Just like when we're looking at the cloud. So when you basically take that cloud, move it around so that you find what's the angle that gives you the largest variability possible, and that axis is basically called feature ID 1 by the model, right? Now, when we do that with that axis, because we moved the cloud around, now we have to take a look at what is the size of the projections of each of the variables or each of the attributes on top of that direction. And some of the variables might have nothing to do with it, and others have more. So that's what it's doing here, right? So for feature ID 1, it's saying the attribute called area error has a kind of a smallish value, right? 10 to the minus 2, 0.05 here. But concave points error has really absolutely nothing to do with this. So this attribute does not help in finding the feature with the most variability possible. So that's what these methods are doing here. And that's why you want to have a couple of things. You first want to understand how strong is that feature ID related to all the other features, because these other are orthogonal, right? The orthogonal projections that you add. So you want to try to find which one is the strongest one, of course, and then what are the variables or attributes that relate the best to the feature 1. And we found out that by using the 7 top attributes with the most relationship to the feature 1 was actually the best model out of this entire notebook, right? So hopefully that makes sense.
Okay, thanks, Marcos. And another question that came in is I responded to it, but I think we could talk about that a little bit. Is handcrafting better than AutoML? And just the starter for that is I said it really depends, right? It's a seasoned data scientist may be able to achieve greater accuracy by combining techniques like you showed here. But AutoML is really to get you a decent model with minimal effort and limited understanding of the algorithms. Any other thoughts on that?
Yeah, no, I think that's right on, and I think that's exactly what I would do. If I have AutoML available, right, that's probably the first thing I want to run just to check potentially for what it comes out with. But also remember that if you're running AutoML, it might be showing you different techniques, right? Different algorithms themselves. In this notebook, I was comparing only logistic regression, right? And using that model straight out from the beginning to end. If you switch to neural networks, then maybe some of these methods might not help you, right? Because neural networks might be able to find maybe some use from those other variables that I left out, right? So it really depends on what you're doing. If you're doing a deep neural network with many, thousands of neurons, then you might want to leave the neurons do what they do and not worry too much about what your clean inputs. But again, I think it's that at that point you achieve that experimentation, right? Trial and error. So you might experiment and try and see what happens. But as you saw today, it might be very useful for you to try some of these techniques versus just letting it run, right?
Great. Another question came in. Is the feature ID also saved in the table? And by this, I'm gathering.
Yes.
Okay.
Yeah. So the feature ID, yeah, they are saved. So the feature ID themselves exists and as a table, and you can export them and you can get them out just like this. So they're a column out of the SVM mod features. So then you can export it, save it to a table, put it somewhere. That's not even a it's a normal thing, right? That comes out of that. Yeah.
Okay. And one last, we have a request actually. Can you do a follow-up presentation that builds on this presentation and discusses overfitting and detecting model regression when datasets dramatically change and the model no longer becomes effective?
Oh, that's interesting. Yeah, we can take a look at that. Yeah, I think overfitting and some of the model regression is something that we wanted to do. So yeah, that's a good request.
Okay. And the last question we'll take is OML for Pi available only on Autonomous Database, or is it available on any Oracle DB Enterprise Edition deployment? Initially, OML for Pi will be GA on Autonomous Database, and we will follow that with on-premise and database cloud service as well. So you'll have both, but it will be staged. And with that, I'd like to thank everyone for attending and the great questions we had. And Marcos, thank you for a very exciting session here on feature extraction. We look forward to the 102 session.
Oh, well, one last question is about OTube. We're going to post it to the Ask Tom site. So exactly where you came to join the session, you're going to see the recording there. And actually, it goes to YouTube on the Oracle Developers channel. Okay. Thank you, guys.